Hello dear students, we take today our third lecture from Analytical Chemistry. The topic of our third lecture is Instrumental Methods of Analysis. Instrumental methods. It's a method of analytical chemistry. It's a measurement of physical properties of analytes, such as conductivity, electrode potential, light absorption or emission, mass-to-change ratio, and fluorescence began to be employed for quantitative analysis of anorganic, organic, and biochemical analytes. Efficient chromatography separation techniques are used for separation of components of complex mixtures. Instrumental methods of analysis. It's a collective name for newer methods for separation and determination of chemical species. The angle of refraction, optical absorption, electrical conductivity of solutions of substances, which is denoted by L, vary within certain limits in proportion to the concentration, which is denoted by C. L conductivity equals K multiplied C. Quantitative analysis of substances is carried out in two ways. The first way, determination the amount of substance according to its physical properties. Second way, determining the equivalence point in photometric methods of analysis on the change in the physical properties of the solutions. Type of instrumental methods. Radiation emission. There is used emission spectroscopy, fluorescence, phosphorescence, luminescence, radiation adsorption. The methods absorption spectroscopy, spectrophotometry, photometry, nuclear magnetic resonance, electrical potential is the method with potentiometry, electrical charge with a coulometry, electrical current with a volt-amperemetry, amperemetry polarography, electrical resistance with the conductometry, and thermal with the thermal gravimetry and calorimetry. Optical methods. The optical range is usually referred to the region of electromagnetic waves with a wavelength lambda of from 100 to 100,000 nanometer. The optical range is divided into ultraviolet, visible, and infrared. Ultraviolet from 100 to 380 nanometer. Visible optical range from the 380 to 760 nanometer, and infrared from 760 to 1000 nanometer. Polarization interaction is divided into refractometry, interferometry, polarimetry, and methods based on measuring the adsorption of light. Molar adsorption method, which is divided on refractometry, interferometry, and polarimetry. Emission methods, which is divided in atomic emission, molecular emission. They are divided. Atomic emission divided into emission spectral analysis, flame photometry. Molecular emission divided on fluorimetry. Methods based on measuring the intensity of light scattered or passed by suspension of substance are nephelometry, turbidimetry, respectively photonephelometry and phototurbidimetry. Visual methods divide on refractometry, polarimetry, interferometry, colorimetry, nephelometry, and turbidimetry. Photoelectric methods divide on photocolorimetry, photonephelometry, phototurbidimetry, and spectrophotometry. Molecular adsorption methods. Depending on the optical range measurement method, width of the measured radiation, the following molecular adsorption methods are distinguished: colorimetry, photocolorimetry, spectrophotometry. Depending on the wavelength, spectrophotometry is distinguished in the ultraviolet, visible, and infrared spectral regions. Another wire is also used: transmission or transmission factor. And the equation takes place in this form: A equal logarithm I0 divided I output, and for transmission factor vice versa I output divide I0. Bouguer-Lambert-Baer law. The absorbance of the solution is proportional to concentration of light absorbing substance and a thickness of a layer, or the relationship between the samples is absorbance and the concentration of the absorbing species. See concentration of absorbing species, where A is the absorption of optical density, eta the molar absorptivity, and C concentration or molarity. In the equation, A equal logarithm multiplied I0 divided I output, and A equal KCL. A is the absorbed light radiation. I0 is the intensity of the light stream entering the cell with the solution of the substance. I output is the intensity of the light stream output the cell. The coefficient of proportionality K is the absorption of the solution with its concentration, and thickness equal to unit. K is the coefficient of proportionality, C concentration, and L is the thickness, which is equal to unity. If the concentration of the solution is expressed in mole-liter, then K, coefficient of proportionality, is the absorption index of the solution containing 1 mole-liter of a substance with a layer thickness L of 1 centimeter. In this case, the absorption index is called the molar absorption or the molar absorption index and is denoted by A. The designating the concentration of the solution in percent, the absorption of the solution is called the specific absorption and denoted E 1% absorption indicator. Specific absorption indicator. Bouguer's law is fundamental in the calculation in the methods of photometric analysis. The concentration of the solution according to the law of Bouguer is equal to, in mol-liter, Cm equal A divided Al, in gram milliliter, C% equal A E multiplied Al. The calculation of molar and specific adsorption index based on a formula on this first and second formula. From this equation we found eta and E. Colorimetry. For the first time, the colorimetric method was introduced into the practice of analysis by Heine in 1849. In the method of colorimetry, the determination of the intensity of the light flux transmitted through a solution of a substance is made by visual means, by comparison with the intensity of the light flux transmitted through a standard solution. The intensity of the light stream is determined by three methods: standard series method, color equalization method, dilution method. Three methods. Standard series method. According to the Bouguer's law, when the concentrations of solutions are equal, their adsorption is equal. A1 equal to this equation, A2 this equation. So we see that A1 equal A2, and so their values is equal. So the concentration of first equal concentration second. Color equalization method is performed on special devices, colorimeters. If we compare two solutions of substances with different absorption of A1 and A2, then with equal absorption, the product of the concentration of C1 and the thickness of the layers L1 of one solution is equal to the production of the concentration C2 and the thicknesses of layer L2 of the second solution. From this equation, A1 and A2, we see that the values of A1 equal to the values of A2. As we see from the equation, their values is equal, so their concentration and thickness is equal. Concentration and thickness of the first solution is equal to the concentration and thickness of the second solution. And from this we can find the concentration of the first solution, which is equal concentration of the second solution multiplied thickness of the second solution divide thickness of the first solution. Hence, concentration of the second solution is equal concentration of the first solution multiplied thickness of the first solution divide thickness of the second solution. In the dilution method, the solution to be analyzed is diluted in the measuring cylinder with a solvent until the color intensity of the solution equals that of the standard solution. Concentration of first solution multiplied volume of the first solution equal to the concentration of second solution multiplied volume of the second solution. Here concentration C1 concentration of the standard solution, C2 concentration of analyzed solution, V1 volume of standard solution multiplied V2 volume of the analyzed solution. Photocolorimetry is a photocolorimetry measurement of the intensity of light fluxes is carried out using photocells. In photocolorimetry, for work using special devices, photocolorimeters. For example, we can see on the picture photocolorimeter FEC-M. It's this and FEC 56M. There are different types of photocolorimeters. Photocolorimeter FEC-M has 5 light filters. Photocolorimeter AMF 69 has 5 light filters. Photocolorimeter FEC 56M has 9 light filters. Photocolorimeter FEC H57 has 11 light filters. So we can see that each of these photocolorimeters differ from each other with a number of light filters. Light filters have a narrow bandwidth and are used to highlight the special region, the maximum absorbed by the substance. For example, for determination of iron 3 positive of 2 regions salicylic acid, determination of iron with the salicylic acid of 2 regions salicylic acid, which is the value of E equal 1.6 multiplied 10 in C degree, and potassium rhodanide, in which the value is equal 7 multiplied 10 in 3 degree. The second gives greater sensitivity. The determination of iron 3 positive with potassium rhodanide is better to be carried out not in an aqueous, in which the value is equal 7 multiplied 10 in 3, but in an acetone medium, which is the value is equal 1.5 multiplied 10 in 4 degree. Since with the use of the second solvent, the absorption of the complex is twice as large, as we see from the difference. In the general case, the sensitivity of the photometric analysis is determined by the formula C minimum is equal A divided EL, and from this we found their value. Setting the minimum absorption A equal to 0.01, at which it is still possible to carry out the analysis at the thickness equal 1 centimeter. For example, in the photometric determination of iron 3 positive using potassium rhodanide in water as a solvent, the minimum detectable concentration of iron we can found from the equation C minimum is equal 0.01 divided 7,000, and we can find the value, which is equal 1.4 multiplied 10 minus 6 mole liter. It was the last information of our third lecture. Thanks for attention.